Welcome to Chemistry 152. I'm Professor Dr. McDonald, and in this semester we're going to spend a lot of time talking about how the concentrations of chemicals in a solution affect chemistry itself. Things like how fast a chemical reaction occurs, if the chemical reaction creates a lot of products, or if the chemical reaction occurs at all, depending on the concentration and properties of those chemicals. This chapter is a little different. We are going to talk about the concentration of chemicals and how they affect the solvent itself. So, in order to cover that, a lot of this chapter is essentially a review of 151. And in fact, if we'd done this correctly, this chapter probably would be tucked into 151, but we just don't have room for it. So we're going to do it here. We're going to use this as a way of reviewing what a solution is, how solutions work, and what kind of concentration calculations we make. This section, we're going to just spend this time talking about how solutions come together and the attractive forces that make them work. So first of all, a homogeneous solution means an evenly mixed solution. So when you add salt to water and it dissolves, we can no longer tell the difference between the salt and the water. It looks like one evenly mixed solution. The salt is always going to be the solute, because it will be the substance in lesser amount. The solvent is always going to be the substance in greater amount. For us, that's almost always going to be water this semester. We will talk about a few other examples in this chapter, but 99% of the time this semester we will be in water. So anytime we talk about gas and liquid solubility, refer to it as miscibility. So, for example, fruit juice, ethanol, those sorts of things mix in water pretty well. CO2 to some small extent. Things that do not mix are called immiscible. So, for example, oil and water here. You could also argue that CO2 isn't really miscible because it does bubble out. But, we can make it dissolve to a certain extent. When we talk about solids and liquids, we mean solubility. So, solid doesn't mix is called insoluble. Solids that mix are soluble. So, on the right, we are adding something, and as you can see, as we add it, it is precipitating out. So how do we determine if these things are soluble or insoluble? Why do some things mix and some things separate? We talked about this a lot in 151. Specifically in chapter 11, we talked about intermolecular forces. When there are attractions between forces, they will stick together. And as a result of that attraction, if the solute is sticking to the solvent, then the solute will dissolve. Now, these attractive forces are not as strong as chemical bonds. However, they are strong enough to control things like solubility, and we'll talk a lot about how they affect the boiling points and the melting points of certain chemicals. So the most common attractive force we're going to talk about is dipole-dipole forces. If you think about water molecule as a small magnet with a negative side and a positive side, anything else that has that negative and positive side will also stick to water. So ethanol or methanol have that polar magnet on the OH, and so as a result, they stick together. Those two magnets will attract each other and circle around each other in solution. Again, polar is often called a dipole moment. Dipole literally means two poles. It has a positive and negative end somewhere on the molecule. Note, if something is nonpolar, it does not have those positive and negative ends, and so it does not stick to water. It's worth mentioning that all these molecules in this picture have hydrogen bonding. We're not going to talk about that so much, but just anytime you have an OH or NH bond, we have strong dipole-dipole moments because of that hydrogen bonding.